Without further ado, very pleased to welcome Jerry Reiter, who's going to be presenting the next paper.
Okay, thank you, Chris, and thank you very much to the organizers for inviting me to participate in the workshop. So Adam gave a wonderful overview of convex optimization via differential privacy, and I thought I'd give an overview of sort of statistical disclosure limitation side of the way this anonymization problem is thought about, with an emphasis on thinking about research problems and sort of setting the agenda, offering some suggestions that people in the program may want to pick up or completely discard, as they may be. This is work that has been sponsored by NSF, NIH, and Census Bureau over the years, and I gratefully acknowledge that. Let me start off by sort of making a disclaimer or an admission, which is that I'm a strong advocate of public use microdata. And I think there are a lot of benefits to having such data for society. I mean, clearly we all know in this room the benefits for having data for research and policy-making purposes, and that's often what we think about when we think about providing access to data, but I think there are other benefits as well. So, for example, having data that students can train on, right? I mean, we those of us in academia are trying to create the next generation of data scientists, and if they don't have data to actually do things on, then that's pretty pretty challenging to actually train them. And so I find this to be a real benefit of if we can have realistic, if not real, public use data. I think it also having access to public use data enables people like us to be able to develop and assess new methodology. You see a lot of the examples. Every paper seems to have some example based on a data set, right? And often those data sets are public use data sets that are out there. And so having these data sets available, I think, has enormous benefits for us. And then, of course, it just helps citizens understand their communities. I think a lot of times as researchers we think about the research community as the key community to have access to data, but there are lots of people out there who want to do small-scale analyses, look at means and subdomain means and things like this. And arguably, if you think about it, particularly in the US, taxpayers have paid for the collection of this data. They should be entitled to access it in some form, right? And so I'm a big fan of public use data, even in a world where analysis is brought to the data, even in this big data world where we can't be sending around data sets because they're just too big, right? I think there's real advantages to having some kind of small, for example, small random sample with some kind of disclosure protections applied to start off with, right? To even know what kind of questions to ask. So, for example, Adam presented a bunch of techniques that can preserve privacy for regressions and things like that. But how do you even know what's the right regression model to ask unless you have some data in front of you, right? Do you want to think about doing some kind of transformation? Should you use a log? Should you use a square root? Should you collapse some categories? Are there enough people of this particular group to support the kind of inference you really want? Are two variables really highly correlated so that maybe you don't want to include both of them in the model as predictors? And these are all the sorts of exploratory questions that we do before we launch into doing statistical analysis. And having some kind of public use data, at least to inform those questions before you start, I think has enormous benefits. Okay? But, of course, the reason we're all here is that it's incredibly difficult to have that public use data because of the threats to the confidentiality of data subjects. And as we all know, we can't just simply strip off the names and the addresses and et cetera and release the data, because there may be opportunities for ill-intentioned users, intruders, to make disclosures of the kinds that Adam talked about and Cynthia will talk about, I'm sure. And a key disclosure attack method is, of course, record linkage, which is another key topic in this workshop. Maybe there's only one Native American woman age 54 working for the state of North Carolina, where I'm from. But if we release something about age, sex, occupation, which are sort of key and race, which are key variables for any kind of social science analysis, then perhaps someone might be able to link to her record to records that are in some external data file and then learn sensitive information about her. Right? That's been a lot of demonstrated attacks that have used record linkage type ideas to make disclosures. And so data providers, of course, are very aware of this, and so I wanted to give a sort of a quick overview of common redaction strategies that many government agencies use, not necessarily to endorse them, but just to talk about them. So the most common technique that government agencies use is aggregation. For example, geographies are coarsened rather than provided at very fine levels. The Census Bureau will release geography at places with no less than 100,000 people. Right? Or incomes will be top-coded. In other words, we don't release a value if it's above a certain threshold, say $200,000. Okay? Or categories are collapsed if there's not a lot of people that are in a particular level of a category, maybe we collapse that. So aggregation is done a lot in statistical agencies, and the hope is that, sort of kind of driven by this k-anonymity type hope, is that we sort of try to make the data, people that could be sort of uniquely identified on a set of variables, make them replicates in some sense on a set of variables. Suppression. The idea there is to take a value and delete it. So if you have a large income, just delete it, not report it in the data set. Okay? Suppression is used a lot for tables where you have some cells that have small counts, just delete them, and then usually there have to be some other cells deleted in order to make sure that you can't just get to the cells from by using the marginal totals, which are often released. Data swapping. The idea here with swapping is that you take one record's values and switch them with another record's value, some subset. So maybe, for example, you find a house that's in county X and another house in county Y, and they have the same number of people in them, and you swap their values, swap all their records. And the idea here is it's sort of a protection by perception in the sense that the agency never tells, of course, which records have been swapped, but an intruder who thinks that they may have gotten a match, well, the agency could say, may have been a mismatch. You don't know for sure if you've gotten a match. Okay, protection by perception. And then adding random noise to values, particularly continuous values, or we might add some Gaussian noise or some other correlated noise to try to make sure that the exact value is released, and as well as try to prevent learning the value within too close of a range. So these are common techniques that are used by many statistical agencies. They're often done at really low intensity. Okay, so nobody knows the swap rate in the decennial census. Well, somebody knows it. I didn't say that well. For the Census Bureau director, John knows it. The Census Bureau director doesn't know it, though, right? The Census Bureau director does not know the swap rate in the decennial census public use files in case he or she is ever called in front of Congress so that can plausibly deny that you know the swap rate for whatever reason. Congress might ask them the swap rate, but nonetheless, the point is we all think it's low because a high swap rate completely destroys the utility of the data, right? At least when you're looking at correlations, associations between the swapped and unswapped variables. In fact, even a 5% swap rate completely screws up the associations in the data. Okay, so we all think swap rates are very, very small, but we don't know for sure. But if they are very, very small, and you think about that, then what kind of protection does that really provide? If 99% of the cases are at their original values, then what have you really done to protect the data? Again, it's perception, which perception I don't think is a strong enough privacy criteria compared to some of the things that we hear about, for example, from differential privacy and others who've created more formal criteria. Suppression creates non-ignorable missing data, typically. Okay, so the reason the value is missing is because of the value, and that's incredibly difficult data to deal with statistically. How do you get right inferences from that is not easy to do. Okay, and in fact, a lot of suppression applications really they delete a lot of the data. So I've worked or advised on transportation statistics, where they have these tables and they suppress like 40% of the cells in the tables. You know, what have you got left, right? I mean, you can't learn a whole lot from that. And so that creates serious problems. And it's not at all clear to me that suppression for tables actually is protective enough. And we see some papers out there that have been able to get pretty good estimates of the suppressed cells using information that are available, say, from previous years or from totals or auxiliary data. So it's not clear that suppression protects enough, particularly at low intensity, and at high intensity it really hurts the data. Aggregation, so aggregation, the types of analyses that you can do are valid at the level of aggregation, so that's quite useful. But anything lower than that, of course, you run into ecological fallacies. You know, relationships at a higher level sort of may not apply to relationships at a lower level. Okay, and so that's difficult. And in fact, very often what we're really interested in are tails, right? The income tail, low and high. That's really where things are, you know, that's where the action is in terms of social science analyses. Right? Or in HIPAA, which is the law in the United States that safeguards privacy of health data that can be shared. One of the criteria in there in what's called the safe harbor provisions is that you shouldn't release any ages if they're above 90. Okay. Well, you know, we are often interested in the elderly, very old people, and so you can't get that information under top coding. Okay. So those things have problems. With adding random noise, well, I guess a lot depends on how you add the noise to the, again, this is to data values, not to outputs. And you know, there are some analyses where you can unwind the noise with specialized techniques. Of course, that does require the user to implement those specialized techniques. And most users of public use data, particularly those three sets that I talked about, maybe not the research set, but the student set and the community set, you know, that they are not going to implement a measurement error model to unwind the noise. It's just not in their wheelhouse. And so we'd like to have techniques where they can focus on their science and do their analysis the way they've always done it, and not have to try to figure out learn some new technique in order to unwind a disclosure treatment that's been done to the data. Right? And so that, anyway, that's a personal philosophy, but you know, I'm sure others may disagree there. So moral of the story is that I don't think the low intensity perturbations are protective enough, and whereas high intensity perturbations can really degrade the quality in ways that are very difficult to unwind. So I'm sort of the opinion now more and more that these common existing techniques they're just not going to be good enough for the privacy settings that we face these days. Okay, so now I've been negative. Let me try to be a little more positive. So what about a possible approach? Well, this is an approach an idea that was suggested back in 1993. It's called synthetic data. And the basic idea is to release simulated data, to build models that describe relationships in the data and then generate draws from those models, new values from those models, and release the simulated data. The hope is that we could preserve the overall structure, the overall global relationships in the data, but sacrifice, you know, for example, really high order interactions, which if you think about it, sort of a really, really high order interaction essentially identifies an individual. Okay? Now, how you actually generate the synthetic data, there are different ways. Sort of Rubin's proposal was actually to use sort of Bayesian statistical models to draw from posterior predictive distributions and then generate new data that way. That idea has been expanded and extended. So for example, you see now people trying to use differentially private models to generate synthetic data. For example, John About and supervised or worked with people at the census to create On the Map, which is a synthetic data set that, well, not fully synthetic, but pretty close, that essentially uses a differentially private data synthesizer. And certainly there are others in the community who are trying to think about other approaches besides Bayesian modeling to generate synthetic data. But what are the potential advantages of this approach? So if every record is simulated, then it really doesn't make any sense to do a record linkage attack. Right? You can't go and look at a simulated record and link it and say that's Jerry, because it's not. It's been simulated. Okay? And so that, you know, for a large part thwarts one of the main attacks that's out there. But that doesn't mean it has zero risks. There are definitely risks, and I'll talk about some of those. Okay, it could preserve associations, keep tails. You could enable small area estimation. A lot of the sort of downsides of the techniques from the previous slide can be mitigated, which I find really appealing. And another feature, which is not talked about a whole lot, but is possible, is a lot of surveys are collected with complex survey designs, which have survey weights attached to them. So in order to do a proper analysis, you need to account for the survey design. You need to account for the weights. And accounting for the weights is not easy. Okay, for point estimates, it's relatively straightforward a lot of times. But getting standard errors correct is really quite difficult. And we often just kind of throw our hands up and do some approximation that is an asymptotic approximation, and who knows how it really does in real small-scale data sets. Okay, but with a fully synthetic approach, at least the Rubin approach, you can actually release simple random samples, and so the user doesn't have to deal with the weights, which I think is a really appealing feature. So there are a few data sets out there that have been created using this fully synthetic data approach I mentioned on the map. Well, that's a partially synthetic data, but there's this synthetic longitudinal business database. So this is a database that I'll talk about in a little bit, but I was involved in the creation of. It's essentially a annual snapshot of all the business establishments that have been around in the U.S. Okay? There's a synthetic survey of income and program participation, which John supervised the creation of. The survey of income and program participation is the largest survey of people on public assistance in the United States, and it's got thousands of variables, actually, when you look at all the topics that are supplemented from the main survey. But what John and his team did was actually link data from IRS records, earnings records, Internal Revenue Service, sorry, link earnings records data to the original SIP cases. But the IRS said, well, there's no way you can release that data. That's too risky. And so they said, well, how about if we synthesize it? And so they actually created a data set where about 600 variables are synthesized. There's actually about 5 or so that are left alone. Is my right about that? It doesn't.
Correct version, it's just sex and who your spouse is.
Okay, so 2 that are left alone. So it's barely partially synthetic. It's basically fully synthetic for the most part. Okay, and that's a really ambitious project. With think about modeling 600 variables and creating synthetic versions of those. Really, really amazing effort. So what I wanted to do is just tell you, kind of give you a little bit of data, since the synthetic data world is kind of focused on trying to create these public use files. So I wanted to show you some of the outputs that can result from doing these sorts of synthetic data sets. So the longitudinal business database, let me talk about that. So this is a database that could deal with business dynamics, job flows, market volatility, industrial organization. A lot of researchers go to the synthetic LBD to try to address these kinds of questions. The only, before we started, the only way you could get access to these data was through the research data centers that the Census Bureau sponsors. Well, back then there were about a dozen of them. I think they're up to 24 at the moment. So they're growing, but still the point is that there's only a small number of them, and in order to get access to the data, you need to apply, get special sworn status, which can take months or longer, and of course physically go to the research data center, which if you're lucky enough to have one near you is not too hard, like we have one at Duke. But if you are not, then that involves leaving your family and moving somewhere for a few months, and that's, of course, not good. And so anyway, that's the LBD. It's an economic census that covers all private non-FAR business establishments. It's more than 30 million individual establishments. It starts in 1976. It's updated annually thereafter. By the way, this is data that's protected by U.S. Code Title 13 and Title 26. So it has very, very precise rules. Basically, you can't release a drop of real information in this data. Even the fact that an establishment filed taxes, I didn't say that, the data come from tax records. Even the fact that an establishment filed taxes is protected. So really, if you're going to release any kind of public use file, all the swapping and the top coding and all that sort of stuff, there's just no chance to do it legally. So you have to do something that's fully synthetic to have a prayer. Okay? So this is kind of the general approach that we use. So so let's suppose that we have some variables that we're trying to synthesize, we're trying to create. We'll call them y's. Some variables that are left alone, call them x's. In our case, x's are going to be things like what NAICS code you're in. We're not going to synthesize that since that's already released by the Census Bureau. Counts of that are released. And essentially, we're going to try to estimate a joint distribution of all these variables. Okay, now this is a pretty high-dimensional problem, right? Because we have, when the establishment came into existence, when it went out of existence, if it did. We have the payroll for every year, the number of employees for every year. You'll see we have a bunch of other variables too. So thinking about some big non-parametric joint distribution is pretty challenging. So we choose to model it sort of in a sequence of conditional models one at a time. Okay, and what some of those models, we use things like Dirichlet multinomial distributions, where we can tweak the prior distributions to try to embed some confidentiality protection, regression modeling, CART-type models, things like of that nature. Okay, it's challenging because there's a lot of structure that you have to respect. You can't have a payroll in a year that you're not in existence, right? And so you have to design this whole mechanism to respect all those sorts of things. Okay, these are the variables. Just quickly, I mentioned some of them. You can see we have a mix of continuous, categorical, binary variables. We've essentially synthesized a longitudinal history of payroll, employment, and multi-unit status, which is whether you're part of a firm, yes or no, from these models where, we fix the state and we fix the NAICS code. We actually, in the first version, did not release state. And that was primarily a marketing ploy because we had to get approval from the Internal Revenue Service and the Census Bureau, and we just kind of wanted to get this going. And so we thought if state wasn't on there, they might feel better about it. Okay, so those are the variables. So we basically generate these models building up one at a time. We sort of first predict the year which the establishment came into existence, and then predict the year it went out. Okay, and those are done from multinomial models pretty much with Dirichlet priors. Then we essentially predict whether they're active or inactive, whether they're part of, you can be inactive means you sort of in the middle suddenly you stopped and then you started up again. Okay? Whether they're part of a firm or not, that's multi-unit, like the local McDonald's establishment is part of the McDonald's firm. Okay? Then again, annual employment, and so we do this sort of 1 year at a time, conditioning on the previous years. Okay, so what are some of the analyses that can result? Here's some overall summaries, and these are sort of the types of analyses that people are interested in doing with these kinds of data. So job destruction, okay, so sort of how many jobs are being lost? Okay. And there's a complicated formula for that the economists have come up with. I didn't come up with it. We just applied their method on their formula on our data set. But you can see that we actually track the patterns pretty well. The blues, the actual LBD, the green and the red are two implicates of the LBD. We don't hit it all the time. There are modeling assumptions, and sometimes we're off. We started off wrong. But we more or less track the pattern with occasional missteps here and there. Yeah, Sophie?
Yeah, what's an implicate?
Oh, sorry. An implicate is we repeat the process 2 times of generating synthetic data.
Okay, so it's two.
So each implicate is 2 separate synthetic data sets. The theory, synthetic data grew from a sort of a utility first perspective. It's sort of a Joseph to kind of steal a little bit of his talk maybe, or advertise his talk. That's what I said. Because it was sort of originally developed as, okay, well, how can you get valid inference properties from synthetic data? And then let's think about the privacy properties, as opposed to how can you have formal privacy properties, and then let's think about the inference properties. And so in that original perspective, the idea was to release multiple implicates to allow for the uncertainty due to imputation, due to synthesis, to be passed on to the analysis secondary inference. Okay, so that's what the multiple implicate. The synthetic SIP has multiple implicates, 16 of them. The LBD, the first version, had only one. Whether the second version has more or not is to be decided. But anyway, point here is that they're reasonably consistent results. Acquisition events weighted by the number of employees. Again, this is something that the economists would be interested in. You can see the massive spike in 1982. The synthetic data replicate that. But it's pretty good, right? I mean, it's not perfect. It's off. But this is not something we set out to capture by any means whatsoever. This is a complicated function of firm structure and changes, annual changes, and things like this. This one we don't do quite as well at. Divestiture events, but you can see that overall the trend is mostly captured, although you can see we failed to hit a few big spikes in 91 and 81 and things of that nature. The firm size, how many firms are there? How many establishments are there in particular firms? So here's a histogram that you can see. Again, we do reasonably well in the synthetic LBDs. The orange, the actual LBD is the blue, but it's not quite perfect. You see that there are some establishments, for whatever reason, that are part of firms and they have 0 employees, which actually doesn't really make any sense in the data. That's another thing that all this, just practical experience and is a research topic. Most of these data sets, the real world data sets, have all sorts of crazy things in them. Right? We see establishments that have 2 employees, 2 employees, 3 employees, 2 employees, 10,000 employees, 2 employees, 3 employees. That's obviously a data error. And that just completely mucks up everything in terms of when you're trying to build models. Right? And so how do you deal with that? So we have to kind of do some cleaning of the data before we even get going. So how do you think about embedding that sort of cleaning process in some kind of formal privacy framework? Or that's an interesting research challenge, I think. Okay, and even just to give you a little more detail on that tail, you can see even out here we do reasonably well. Again, not exactly. There will be some differences for sure, because it's a synthetic thing. What we're doing basically is simulating whether each establishment is part of a firm, simulating what firm it belongs to, and then aggregating up to count how many establishments are in each firm that we've created.
All the reds are smaller than the blues.
All the reds are smaller than the blues. Well, I mean, some of that is over here, and that's 0.
The one you just.
Oh, this is just the one I just said. This is the tail of this graph. This is the tail out here of this, because you can't see it because of the scale of the y-axis. Okay. Anyway, that just gives you an idea of the types of analyses that we hope to be able to enable with these synthetic data sets. Okay. So what about the disclosure risks? Well, I mentioned that because every data is simulated, these sort of record linkage attacks they're nonsensical. They really don't make any sense. And so I think that in general the rest of identification disclosures should be low. They're not 0, but they should be low, right? And the reason why they're not 0 is because there are opportunities for the synthesizers to sort of create data that still lead to disclosure. So just a quick example. Right? This is from a paper that we have in Transactions on Data Privacy, I think, where we actually try to compare statistical disclosure risk, posterior probabilities of identification, to what would be done under differentially private, and just sort of looking at the epsilons and seeing how they compare to statistical disclosure probabilities, and seeing when they match up and when they don't. Anyway, here's a simple example. You have a data with 4 binary variables, and obviously this is stylized. And there's you've created synthetic data, you've generated from say a multinomial model, and you have one case that has 0, 0, 0, 0. Okay. If you've used a multinomial synthesizer without any kind of prior probability, say you set the prior to something really, really tiny. Okay, just use a multinomial. Forget prior. Use a multinomial, that tells you that there must be at least one real data case that had that 0, 0, 0, 0. Otherwise, there's no way you could have generated that. Okay, so that sort of thing, can happen, and that's the kind of risk of identification disclosure that could exist in the synthetic data set. Right?
Why couldn't you generate 0, 0?
Oh, so if I've used a multinomial synthesizer where probability is equal to the empirical frequencies, right? So the probability of generating, let's say there's 1,000 people, n is 1,000 in the data set, and there's 600 of them that have 1, 1, 1, 1, 1. Then the probability in that multinomial for 1, 1, 1, 1 would be 0.6, okay? If I'm in my multinomial synthesizer. If I had one person at 0, 0, 0, 0, the probability would be 1 over 1,000. If I had 0 people at 0, 0, 0, the probability would be 0. So the only way I could generate a 0, 0, 0, 0 in the confidential data is if I had at least one person in the synthetic data, is if I had at least one person in the original data. Okay?
But the risk isn't equal to 1, right? I mean, there could be more than one person in the confidential data that had 0.
There could be more than one person, so the probability would be at least 1. Right? Yes. And I think the more pressing, I mean, with real data, with the types of models we build, I mean, we're almost never, we rarely can saturate it that much, just practically. We make all sorts of modeling assumptions that really cut things down. So in my experience, it's pretty hard to think about identification. But there are attribute disclosure risks, and this is the more serious threat, I think. So we know that synthesizers can perfectly predict some X for certain types of individuals. Right? And then, if so, then the synthetic data will have those true values of X that have been generated. Right? So just an example, with regression trees, if you're using a regression tree to make synthetic data, which is a nice, flexible, automatic method, it kind of removes a lot of the modeling challenge in some sense. But you basically would take an X, well, let me start over. To fit the tree, of course, you would try to predict race, say a 4-category race, from all sorts of other X variables. And of course, it makes a tree by splitting the data into bins. And then you take your X that you have, you say it's synthetic X that's been previously generated, run it down the bins, get into a leaf, and then randomly draw from the leaf, perhaps with some noise added to the leaf. Okay? The idea, though, is that if everybody in a particular set of predictor characteristics has the exact same X, the tree will also generate that exact same X. And so that could be a disclosure. Okay? Related, there may be some synthetic data models that are sort of too accurate in predicting values. So they get right there. Okay? And again, the trees is a nice example of that. If you fit a tree for continuous data, if you draw from within the leaf without any kind of smoothing, then you're actually generating an actual value. Right? You're releasing an actual value. But even if you put some smoothing on top of it, it may be that the smoothing is not enough, that you still get a pretty close estimate of whatever the actual value is. Yeah.
I guess just a sort of a question and a comment. Like attribute disclosure is tricky to think about because in some cases what you might be learning is sort of correlations that are there in the population that are exactly the things you want to learn. And sort of distinguishing between that and learning things that are sort of overly specific to individuals is delicate.
Yes.
I think this will come as sort of a plug for Cynthia's talk. She'll talk about the difference. But yeah, I guess I guess I was wondering if you've thought at all about this distinction and you know how you sort of conceptualize it.
Yeah. So well, let me show a couple of disclosure risk slides and then see if I can address that once I get to those. So there are risks, okay? So that is clear. So then the question is, how do we assess them? You know, here's a conceptual framework, and I have to advertise that it's really a conceptual framework because in the types of data sets that I've tried to create, computationally it's an absolute nightmare to implement this computational conceptual framework. But essentially what we're interested in are things like what's the posterior distribution of a true value for some target, the ith target, given what's been released, the synthetic data, some assumptions about what the intruder knows in terms of what information has been released about the generation. In synthetic data, we tend to release all the models that have been used. Sometimes we've released the code that's been used to generate the synthetic data. So we assume that's available. Any unchanged original data, fully synthetic data, there may not be any. And sort of, what I'm going to talk about here is assuming that that this probability calculation is done excluding only the record I. So assume the intruder knows everything but one, which is inspired by the differential privacy idea, but different. And this is not differential privacy, obviously. This is an empirical calculation that's done on the particular data for the particular release, not over all data sets and over all possible releases. Yeah.
When you say the posterior, what do you assume is the prior?
So let me, okay. So this is the posterior we want to compute, right? And so how do you compute this thing? So, well, you just plug through Bayes' rule, right? Which essentially is, take a guess at what the yi value is, plug it in, figure out the probability of generating the synthetic data set that's being proposed for release, and try that for all sorts of different yi's that you have. Okay? So there is a prior that needs to be put in. That's absolutely right. And that's, of course, one of the limitations here is that we don't know what the intruder's prior is. We have no idea. And so the only thing we can really do is just estimate it under what we might call reasonable prior distributions. Okay? For example, we might say, okay, well, let's look at a uniform prior over a sensible range. That sort of reflects the idea that the intruder really doesn't know anything about this yi value. What could they learn from the synthetic data alone? Okay? Or we might say, well, let's use a prior that's based on this assumption that they know everything but one. Maybe they'll actually build a model to try to predict what that final value is. Okay? In my experience, by the way, using these models is often sort of gives worse risk of, lower risk estimates than using the uniform prior, because a lot of times, for example, you have outliers, they're not right on the model, right? They're off. That's the whole point. And the uniform kind of gives more weight to having that value than a model, which would say, oh, your best guess is really quite close to the line, and it's really unlikely to be far away from the line. So that's kind of the idea. So just under best possible, reasonable assumptions, and see what these posterior probabilities are. Okay. Some examples where that's done are in this papers there. And then you can take those posterior probabilities and do all sorts of things with them if you want. So you could ask, well, what's the percentage that are correct if it's discrete variables? And I say, oh, if I say, how many times do I match the true yi? How many times is the true yi the highest probability value? And how often does that happen over the whole data set? Or we could compute ratios of posterior to prior risks, which is sort of kind of getting a little bit towards Adam's point. You might say, there's a prior, if you didn't have the synthetic data, how well could you have guessed this value from just say using the correlation of the correlational structure alone? And then you could ask, well, how much extra does the synthetic data give you over if you didn't have that synthetic data? Okay, so it's kind of gets at some of these issues that we've talked about. And these don't have to be point masses. They could certainly be ranges as well. You could look at, which for continuous data is probably what you really want to do. So it's a point, picking a particular probability of a particular point is, it's sort of silly in some sense, right? You could think about getting, the intruder's best guess would be an expected value. You could figure what's the probability that it's within a certain range that we're interested in, and again, take ratios of posterior to prior on that range. All sorts of summary measures that you could come up with. Okay? So that's conceptually a framework for trying to assess disclosure risks. Some comments on this. Again, they assume a pretty strong intruder knowledge, all but one, right? Which is really necessary for computation in some sense, because without that, it gets really difficult to actually compute these probabilities, because the space of possible things to worry about is huge. I mean, just huge. And so, it is a strong intruder. People, when I talk about this, they say it's an unrealistic intruder. There is no intruder who knows all but one for one particular target, but it does enable us to do computation, and it can be viewed as sort of a worst-case kind of scenario. This is an empirical, quote-unquote, evaluation, because it's based on the actual data and the synthetic data that's being proposed. So it doesn't have the formal privacy guarantees In particular, there's no notion of composition at the moment. Okay, and so that's a weakness. It's sort of a, you know, what can we do, best we can do kind of approach. It does struggle computationally when the target has many variables. So some of the data sets that I've worked on, the LBD is pretty high dimensional. I'm trying to think about creating a synthetic data set for the Office of Personnel Management, the U.S. Government's Human Resources Agency. And you know, there we have every federal employee going back to 1988, and we have all sorts of information on them. OPM wants people to access the data. They want researchers to get involved. They're thinking about trying to create a synthetic data set. You know, when we compute these kind of measures, we get values like 10 to the minus 30. You know, because you have so many variables that you're trying to multiply together to compute these probabilities. I mean, you know, what do you do with that? So this is a conceptual framework. In practice, you know, disclosure risk assessment has been kind of ad hoc. Okay, I mean, it's been ad hoc. It's been things like look at the max value on the synthetic data and see if that sort of is similar to the max value in the real data, right? It's kind of trying to get a little bit at this idea, but it's not really the same.
It's always computed under the assumption that the model it shows to synthesize is correct.
It's always computed under the assumption the model you chose to synthesize is correct. Well, in some sense, you know, the intruder here should use this model, the synthesis model, whether it's correct or not, to evaluate this probability, right? Because this is the model that was used to generate the data. Now, what they do here is a whole other story. But here they should use the synthesis model to evaluate this likelihood. And I mean, it's not correct, right? The model is not correct. And they can't be correct. I mean, it's just, yeah, okay? So it's been ad hoc, and this is an area for opportunity for research. You know, how can we do something a bit more formal? And I'll come back to that, okay? Okay, so that's sort of a review. I want to turn to something a little bit more current in terms of research. You know, the reality is that synthetic data, of course, can't preserve every analysis, and it's the analysis quality is entirely dependent on the quality of the synthesis model. Whatever relationship is in the synthesis model gets passed on. If it's not in the model, it doesn't get passed on. Okay? And it's really hard for the user to know, given just the synthetic data, and frankly, even if they had the code that was used, the typical user is going to have a really hard time knowing whether or not her model, her analysis, sort of faithfully reflects what they would have gotten from the original data, if they'd used the original data. Really difficult to know that. Okay, so it's really hard for her to know if she should trust the synthetic data results. And oh, by the way, I think the similar issue applies for noisy statistical outputs, right? So, for example, you know, again, Adam had this really cool, presented a bunch of really cool techniques for convex optimization under differential privacy. But how do we know whether the positive model that we've put down is any good or not? Right? We can compute it in a differentially private manner, but it may be a lousy fit to the data, right? And so how do we know that? You know, maybe the relationship has a quadratic relationship, and we threw in a linear model. So we might get a close estimate of a completely terrible fitting model, right? And so I think these issues are big. They apply to every kind of disclosure protection method that's out there. So how do we assess the quality of synthetic data or of any kind of noisy output? And so one idea that we're working on is something called a verification server. Okay? And so the idea is that this is a separate system that has the confidential data and has the synthetic data or otherwise redacted data. Or if you want to think about it as a system that has confidential data and a system that generates noisy answers to particular analyses. The user actually submits a query to the system for verification of a particular analysis. So the user says, oh, I wanted to do a regression of the log of variable 3 on variable 6, 10, 25. The server does the analysis on both data sets, computes some measure of similarity, does some kind of diagnostic, and reports back that diagnostic to the user. So, for example, you know, how much do the confidence intervals overlap? Do they overlap a lot, or do they overlap not at all? How far apart are the point estimates? You know, what do residual plots look like? These sorts of things. Okay. Again, I think this is also relevant for noisy model outputs. How do you know in sort of finite samples? Forget asymptotics, because who knows what happens in the real world as opposed to asymptotics. How do we know whether our analysis here is any good or not? The problem, of course, is that reporting these quality measures leaks information about the data. And so it's not easy to think about how you can protect those. And this is where I think differential privacy offers a really strong path forward. So we could imagine potentially having sort of different types of verification for different types of trusted users. So we can imagine having sort of low trust users, people who haven't been vetted somehow, and they would only get sort of allowed to get verification for very specific analyses that are preset by the agency. So maybe regressions or means or things like this. And they would only get broad measures that could be implemented or could be done with differential privacy. So for example, the sign of the regression coefficient, or maybe statistical significance, or some kind of plot of residuals. I'm going to talk about all those. Okay? And because it's a query system where people are asking over and over, there I think we really want to think about a differentially private solution. Okay, so that's a low trust. And then maybe for people who we trust a bit more, we might give them more freedom. They've been vetted, they've been approved, we think they're going to be okay with the data, but we don't have full confidence in them to give them access to the data. Those we might give more freedom to, how much of the confidence intervals overlap, which I couldn't figure out a differentially private measure for, but it's relatively straightforward to compute, okay? And it's really hard to back those out unless you try. And so if we have medium trust, we think people aren't going to try, but we want to prevent this sort of really obvious disclosure. So maybe lightly protected visual displays, things like this. So we're working on developing this kind of system. So let me talk about a little bit what we've done so far for the low trust users. So we've developed some techniques that can give you a differentially private measure of whether the coefficient for the in a linear regression model is the same in the synthetic data or from a differentially private algorithm is the same as the coefficient in the original data model. Okay, and that's based on subsample aggregate type techniques, which you could, for example, use the partial correlation, which has the same sign as the original data, but it's bounded between -1 and 1, so it's really easy to put get sensitivity for it, and essentially compute that in each one, average up, and add the noise. Okay. Significance for regression coefficients, we've been trying to create differentially private t-statistics, again thinking about subsample aggregate, chopping off the tails. We have a way of doing ROC curves in logistic regression, and we also have a way of getting plots of residuals versus predicted values for linear and logistic regression. And I'll talk about the last one briefly here. So here's kind of the idea. So with linear regression, of course, the model theoretically is unbounded, right? And so that creates a big headache. Residuals can go from -infinity to +infinity. The predicted values could, unless you have bounded x and bounded y, the predicted values could stretch from anything as well. And so it's non-trivial to think how you could release a residual plot that satisfies differential privacy. And for that matter, you don't want to just release the residual plot. Maybe that's obvious, but if you just release residual plot without any noise, someone could, they know an x, and then they have the regression coefficients, and then they figure out the predicted value, and then they could back into the y, sort of obvious, right? Okay, so anyway, what we do is using the sparse vector technique, we sort of have a differentially private algorithm to approximate a bounding box for the residuals that sort of encapsulate a high percentage of the data, say 95% of the data. Okay? And you need that box, again, because otherwise it can go off to infinity, right? Overlay a grid on that box, compute what I'm calling residuals in quotes, which is basically the true data value minus that should be the true x values times the synthetic or differentially private, whatever, the beta hat that you've got from your algorithm that you think is safe. So I'm calling it residuals because it's not the true residuals, because they're not, that should be BOLS from the original data for a true residual. Okay? So these are sort of the residuals, and the predicted values are computed kind of the same way, and then essentially figure out how many are in each one of those grids and use the Laplace noise and perturbed accounts. using the Galois algorithm, for those of you who know that. If those of you don't worry about it. Essentially, it will create a noisy plot, which hopefully will replicate the patterns and the original residual plot. Because that's the whole idea, is patterns, right? When we do plots of residuals versus predicted values, we're looking for patterns that suggest the regression assumptions are violated. Okay, so that's what we're going after. Okay, so let's give you a few examples. So here's just three very simple linear regressions. These are what residual plots would look like if you had data that perfectly followed the normal assumption. That's on the left, A. That was heteroscedastic. The variance is increasing with the x. Okay, that's B. And then a nonlinear model. This has a y. The mean of y is x plus x squared, with some coefficients in there. Okay, so these are what the residual plots would look like if you had the original data, the confidential data. And we know as regression modelers that we would want not to just fit a linear regression to this, because we wouldn't trust the standard errors, for example. We'd probably want to take the log of the y first and then fit the model. We know here we wouldn't want to fit a linear model with y on x, because it would give us completely meaningless predictions. So we want to put a quadratic term in there, for example. Okay, so we know how to do that if we had this information. So using the algorithm I just presented to you, here are some results when epsilon is 1. Oh, this is n equals 1,000 data points that are generated. Again, for the first one, from the linear model, there's x is a uniform distribution that went, I think, from 0 to 50. It didn't really matter too much what x was. Okay. Anyway, so here's what you see. So this is a noisy residual plot now, and you can kind of see it looks pretty good, right? In the sense of it's telling you that the model assumptions are not too bad. Oh, by the way, I should also mention these are for illustrations, so we're actually using the actual values of the beta from the OLS for the illustration. You obviously couldn't use the actual values for the beta from the OLS, because that would fail the differential privacy. You would use the synthetic data value or an Orsheffet type estimate, which we plugged in, by the way, and they look terrible on this sort of plot. Anyway, so this is just for illustration. So you can see this looks pretty good. You can see our bounding algorithm. It captured not all the data, right? This goes up to 4 and -4, 0 to 55 on the axis for the true data, and we go from -60 to 60, and all the way up to there. But it looks pretty good. With epsilon 1 heteroscedastic, you could see that pattern. If you got that plot, you'd know to take a log. If you got this plot, you'd know that your linear model was terrible and you'd want to do something else. So it's giving you information. Epsilon 0.1, obviously we start to degrade. But you could still see that looks reasonably good. You could still make out the heteroscedastic bit there. It's sort of there, right? It's harder, but it's there. And the quadratic is definitely a lot harder to see, but if you're trained to do that, trained to look for these things, you might be able to see it. Okay. Anyway, so the point is, we have some potential to sort of understand, to learn whether the model that we've put down has any fits the data reasonably well. Okay. I think I'm running out of time. So, one of the things, so limitations, of course, some of our methods rely on subsample aggregate, which could get different results of the original data, particularly when there's highly influential points. That's the thing about linear regression, right? You can have one data point that just makes your line go from this to this. So it's incredibly sensitive. That can really foul up subsample aggregate type stuff. We have composition if the regression coefficient estimate satisfies differential privacy, but we don't know what the properties are for other estimates like synthetic data, for example. And then, a real tricky part here is individual users often want hundreds of analyses. They want to do lots and lots and lots of analyses, but you've got to give them a budget, presumably, and that budget will be exhausted very quickly because these methods we have right now, you chew through a lot of epsilon to do what you want to do. Okay, so this is a real challenge, to figure this out. Okay, quickly, some opportunities for research. So these are some questions that I think would be interesting, potentially. So, we have this model-based synthetic data, and, Adam pointed out this one paper that shows that there's, under some conditions, that Bayesian methods can satisfy differential privacy. Whether those conditions are reasonable or not, I'm not sure. But 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 can we prove anything about synthetic data without using differential privacy? I don't know. We have this all but one. What about all but k? Where k is greater than 1, obviously. Might that be useful? And we've done some empirical work that suggests the risk. I mean, they nosedive except for massive outliers. Then it's not much you can do about massive outliers with anything, frankly. But the risks nosedive very quickly. What if they don't know anything? Might that be a useful thing to think about? Mostly because for the types of data sets that I've been working on creating, I would love to implement a differentially private algorithm, but I don't know how to do it without sacrificing some of the richness of the data. Can we sort of make model-based synthesizers with privacy guarantees baked in, even for LBD-like data? So maybe rather than conditioning on the actual data, could we condition on intervals, for example, safety intervals? So fit models that are, instead of y given x, y given a to b, ai to bi for all the i's. So then the most that the user could learn would be the ai to bi's. And so maybe there's a path there. It's connected to some of the blowfish privacy ideas. A lot of these data sets get updated, like the LBD gets updated. Each year there's a new data set. And so, ideally we would like to update the synthetic data too. But how the heck do we do that in this context? How do we figure out the risks associated with that? I don't know. That's really, really hard unless the data have some composition property. Verification measures, I mentioned that you could blow through budgets pretty quickly, so it'd be nice to have better, more refined methods for that. Other types of quantities besides the very limited methods, quantities that I put forward. And then what are the risks that if you have one of these measures, they're differentially private, but what are the risks when you have other external information like a synthetic data set that's not differentially private? How does that play in? Again, releasing outputs, sort of building on Adam's stuff, particularly with these models that have really high sensitivity like regression and the like, modest samples, they could be massively impacted by one individual. And so how do we actually release outputs? That to me is a really important challenge. And then last thing, which I'm not sure is the purview of this group, but what is disclosure in the modern age? I mean, a lot of the laws in the US anyway speak to re-identification, but maybe that's not the right thing to focus on, right? Maybe the thing to focus on is more about attribute disclosure and just give up on re-identification. I mean, in some sense, I think re-identification was put in because it was something that was, sort of clear and well-defined, whereas attributes, everybody may have their own belief as to what's an attribute disclosure. Is the fact that you know that I have a TV, is that a disclosure? I don't know. Maybe it is for me. Maybe it's not for you. And so identification is clean. But, focusing on identification makes us do a lot, I think, makes us have to do a lot of other things. And maybe there are other methods that we could use if we weren't worried about re-identification. So, conditioning on intervals might be an example. I'll close there, and I know I chewed up all my time, but I just got too excited. So I'm happy to take a few minutes of questions. I know we're running close to lunch, but.
Indeed, Jerry. Fascinating. So, yes.
Yeah, I have liked the talk very much because it is on real data sets and real problems, and then you can see the complexity of the thing. Especially the question on the updates that you raised at the end is a serious one, and if you move to continuous data, like streaming data, it's even worse. So there are lots of challenges for a program like this to tackle, and I agree with that. And then regarding the idea, so I like this idea of verification servers when I read about it long ago, and it's a really good one. Now, but if the answers of the verification servers are also not quite true, in the end well, first I am cheating you because I'm giving you synthetic data, and then I'm not telling you the truth regarding how far the results are from the real ones. So it's sort of, wait a moment, I will cheat you once more.
Yeah.
I don't know, maybe users may be a bit are reluctant to this solution. What is your opinion on that?
Well, it's a good point. So the question was about, if you get verification, you're getting a noisy verification measure, at least for the low trust users. The medium trust users, maybe we can give them something more fine-grained. But anyway, you're getting a noisy measure, so how might users react to that? Well, I mean, that's the price of privacy, right? What are you going to do? I do think, though, that it might be easier to kind of muck up some of these verification measures than it might be to provide noisy answers to some of these models. Like significance, you could have a really complicated model, which is really hard to get a sense of what the sensitivity is. Just to even compute it, like Adam was saying, some of these neural network type models, just even to compute it. And whereas, you might be able to figure out the sign of the coefficient. Is it the same or not? In a relatively straightforward way. Or significance, maybe you can get a good handle on that if you can collapse everything to t-statistics and do something differentially private t-statistics. Okay? So in that sense, I think there's benefit there. And I do think there's value added compared to having nothing. Right? Again, you're just kind of hoping that your model is halfway decent if you're analyzing synthetic data or throwing a model out there and getting a differentially private answer to it. You're hoping without a whole lot of backup that it's good, and this gives you, at least for some models so far, some opportunity for backup. But I do think there's lots of room for improvement. This is really, early stage on all this stuff.
I guess just to add on to this sort of last point is that for a lot of these methods, sort of differentially private or not, if these randomized methods, you can compute, say, things like confidence intervals without any additional disclosure, just based on the algorithm. You can say, well, okay, we know the kind of perturbation that was introduced. We can say it's, with 95% probability, it's within this range, and so you can, in some cases, without additional privacy loss, provide extra information that help people interpret the output, and that might get partway towards answering Josep's the issue Josep raised, where you're not even entirely you don't even have complete certainty about the feedback you're getting for verification. Hold it, just a sec, John. So I just wanted to say one more thing that wasn't related to Josep's question, which is that, but was related to something you were saying about the knowing one versus knowing k, or not knowing one versus not knowing k points, and things like that.
Yeah.
So there are a few papers that have looked at sort of various formal guarantees, assuming certain types of knowledge from the attacker, right. Where you sort of try to come up with a framework that allows you to specify maybe a class of priors or something like that.
Right.
I would say that sort of there are a few papers out there on topics like that. There's probably a lot more to be said there about understanding the role of the kind of side information. That said, you have to be careful, given that you don't necessarily know ahead of time what other types of information will be released by other sources in the future.
I suspect you're going to talk about confidence intervals versus intervals of the...
Wanted to qualify what Adam said, is that whatever privacy-preserving publication system that you use to reveal to the user the information necessary to make the inference is modified by the differential privacy or formal privacy distributions. And if you disclose all of that, then I agree with you. But if you get a coefficient and the probability model that was used to protect the privacy, but you're missing the intrinsic measure of error for that coefficient, then you can't do it. So I think you were just assuming that the published output would include the conventional elements used to test the hypothesis.
That's sort of what I had. I guess it was just a more general point that very often you can, given that the process, the randomized process that was used to generate the output, whatever that output that was, you can often associate extra things like confidence intervals to it without any additional
With
disclosure.
proportions, that's a lot more straightforward than with other types of models.
Yeah, right.
Okay.
Yes.
I think we'd better wind it up here. We have a final session today when we can return to some of these issues. Jerry, do you want to have a final word?
No, I've taken too long already. Sorry.
Okay. So, well, thank you very much.